Hi everyone. This tutorial is about some concepts related to energy and how energy changes and is transformed in living systems, so within cells, within an organism. And this corresponds to a note called the Energy Note 1, which is in the Unit 1 Part 3 folder on Edmodo. And I want to begin our look at energy by talking about an important concept, and the concept is called metabolism. So metabolism is probably a word that you've heard before. We all talk about whether we have a fast metabolism or slow metabolism, but most people don't know what the word metabolism actually means. So metabolism is a biochemistry term. It's a physiology term, and it is a description of all of the chemical reactions that happen in our body. So at any given moment, we have thousands of different chemical reactions happening inside our body. And these reactions all have a rate or a speed. And the sum of all of these different reactions and their rates are what we commonly think of as metabolism. So in this tutorial, you're going to learn about some of the terms and the more difficult concepts that are related to energy as it changes through various metabolic reactions. Now, I mentioned that there are thousands of different chemical reactions happening in our body that the sum of all of them make up metabolism. We can take those reactions and subdivide them into two general types. Chemical reactions can be classified as catabolic, or they can be classified as anabolic. And I've chosen to put in a couple of pictures of playing cards here. And you can see in the picture for the catabolic reactions that it's just a pile of random cards. There's no organization to this pile of cards. They're just strewn about on the top of a table. But if you look at the picture of the cards in the anabolic reaction section of this slide, they've been highly organized into a house of cards. And so this is an analogy for what happens with chemical reactions. Remember that chemical reactions involve taking reactants and changing them into something new, changing them into a new product. And reactions will involve either taking molecules and breaking them up into smaller molecules, and therefore releasing energy because there's energy stored in chemical bonds, or reactions involve taking a lot of smaller molecules and packaging them together, putting them together into more complex molecules. And this tends to be an energy requiring process. It takes a lot of energy to put molecules together. So this is where energy connects to our look at metabolism here. Chemical reactions that involve tearing down or breaking down complex molecules into simpler ones will release energy, and that's our catabolic reactions. Chemical reactions that involve putting smaller molecules together in order to create larger, more complex reactions require energy. You have to put energy into those reactions for that to happen, and so these are our anabolic reactions. And one way you can remember this is you probably know what anabolic steroids are. So anabolic steroids are taken by people who want to build up muscle. So they're trying to create larger, more complex structures out of smaller structures. These are anabolic processes. And again, these are energy requiring processes. Now, we really can't do a study of energy in biology without considering the two fundamental laws in the universe that are related to what happens with energy. So these two laws, the first law of thermodynamics and the second law of thermodynamics, written here. You may have heard of the first law of thermodynamics because it's a really fundamental law that a lot of people are aware of. And this law tells us that energy cannot be created or destroyed. It can be changed, it can be converted from one form into another. For example, electricity can be converted into light energy. The energy of moving water can be converted into electricity. So we know lots of ways that energy can be changed from one form to another, but the law is that you cannot create energy from nothing, and it's not possible to destroy energy. So that's a pretty fundamental law. Basically, the amount of energy that we have in the universe is a constant. The second law of thermodynamics, however, tells us that the content is diminishing. Now that seems to contradict the first one. It's not that the amount of energy is diminishing. What's diminishing is the amount of usable energy to us. So the second law of thermodynamics tells us that with every energy conversion that happens, some of the original energy gets converted into an unusable form. Think of a light bulb in a lamp, especially the older style incandescent light bulbs. They do produce light from the electricity that's coming into them, but they also produce a tremendous amount of heat. And we lose that heat. It's not destroyed, it's just lost to us. It's not usable energy anymore. And this happens every time there is an energy conversion from one form of energy to another. So what does this all mean to us? Why is this even relevant? We need to be aware as biologists that if energy is diminishing, if the amount of usable energy available to us is decreasing, then this is what's happening in our cells. And in a way, I like to think of this as kind of explaining the process of aging. As we grow and get older and older, we lose particles, we lose molecules, and we lose the ability to convert energy into a more usable form. And so this is kind of happening to our universe as well. Our universe is aging. We are diminishing the amount of energy. And this is all part of the chaos theory, which you may have heard of. It's certainly over my head, and I'm not an astrophysicist. It's not something I really have a whole lot of interest in. But this is what chaos theorists work on. They deal with the second law of thermodynamics, and they study what's happening to the universe's energy. So we'll move on and try to relate this to biology. I don't want to go into the realm of physics too much, but we do kind of have to touch on a little bit of biophysics here and a little bit of biochemistry in order to understand what happens to energy in our cells. So the second law of thermodynamics leads us to a very strange concept. And this concept is called entropy. So I found this poster on Google, and it says entropy will continue to increase until enough dark energy is created to rip the universe as we know it to shreds. Have a nice day. So this is part of this chaos theory that as the amount of usable energy decreases in the universe, the amount of free energy we call it, we will eventually cease to exist. Now I think this is a long way away. I don't think we all need to start stuffing money in our mattresses, but eventually this is the theory that the universe will basically burn out. Here's a cute little cartoon just to give you an idea maybe of what entropy is all about. You can see this guy sitting in his office, and on the door it says Department of Entropy. And what do you notice about this office? Well, it's falling apart. And this is the idea, the theory that entropy is increasing in our universe, that the amount of chaos and disorder is increasing in our universe, just like this guy's office. And in this little photo, this shows you that as time elapses, the nice, neat bedroom that you see right here, over time, a spontaneous reaction occurs, and eventually it looks more like this, which is kind of like what my office looks like. As time elapses, everything is going to go towards a greater state of disorder. It will have less organization. And if we want to get it back to a very ordered state, that's going to require a lot of energy input. And it's the same thing that happens with molecules in our cells. Left alone and not being maintained and repaired, cells become disordered and chaotic and fall apart. And it takes energy in order to maintain the orderliness of our cells. Really, overall, our cells and our bodies in general are quite ordered. And it takes a lot of energy in order to maintain that order and prevent entropy from increasing. Now, this picture, I'm trying to get it towards science now and away from pictures that just help you to understand entropy. You can see in this picture you have an ice cube, and the ice cube is at its maximum order. The molecules of water are organized into a crystal structure. Given time, those molecules are going to warm up and they're going to start to increase in kinetic energy. And as they increase their kinetic energy, these molecules are moving around more, they're going to melt. So when they melt and you have this puddle of water, you have no structure. It's very disorganized, it's chaotic. And this would be maximum entropy. So the cube is considered low entropy. So entropy basically is a measure of the amount of disorder in a system. So in this case, the system is the ice cube. In biology, a system would be a cell, or it would be an entire organism, an entire living thing. If it's very, very organized, it has low entropy. As the particles that make up the system become disorganized and chaotic, then we say that system has high entropy. So the puddle of water has very little order and it has therefore high entropy. And in this diagram, I think it shows it even better. If you start out with this very organized group of particles, this is the particles of gas that have been compressed into a very closed container. Over time, those particles are going to begin to spread out. They're going to move between the spaces of the air in the container, and over time, it will look like this. The other example at the bottom, if you toss bricks off a truck, which kind of pile of bricks would you be more likely to produce? This is highly unlikely to happen. A disordered pile is highly more probable. And so this is entropy in the universe. It is far more probable for any kind of particle to be disorganized. That's the natural tendency of particles. It takes a large energy input to organize those particles. So if you look at the bricks, which pile of bricks has higher entropy? Remember, entropy is a measure of the amount of disorder or chaosness. So does the organized pile of bricks have high entropy, or does the disorganized random pile of bricks have high entropy? Well, if you said this one, you're right. So the random pile of bricks has high entropy. It's low organization, high entropy. The stacked up pile of bricks would be low entropy.